So, have you ever wondered how simple diagrams can be used to explain complex semiconductor devices such as transistors, lasers, or even solar cells? So, energy band diagrams are not just lines on a graph, they are the language of device physics. Welcome to part 1 of this series on energy band diagrams. In this video, I'll be breaking down two key questions. The first one is what are energy band diagrams, and the second one is what valuable insights you can gain by analyzing them. So by end of this video, you will be able to understand why these diagrams are a powerful tool used in order to gain better understanding of device physics. So let's get started. So the first question is what are energy band diagrams? So these are nothing but a plot of electrostatic potential energy versus the distance. So in particular, we are concerned about two energy levels. So the first one is the bottom of the conduction band, which is denoted by EC, and the other one is the top of the valence band, which is denoted by EB. So apart from these two energy levels, we draw one more thing that is called the Fermi energy level. So this is denoted by EF. So EF is just a statistical concept. It comes from Fermi Dirac statistics, and what this tells us the balance between the electrons and hole concentration in the material. So if EF is at the middle of the band gap, so the band gap is actually given by the difference between EC and EB. It is denoted by EG. So if EF is at the middle of the band gap, it means that your electron and hole concentrations are equal. So if EF moves closer to your conduction band, that means the concentration of electrons is greater compared to that of concentration of holes. And similarly, if EF moves closer to the valence band, the concentration of holes is greater than that of the electrons. So this concentration of electrons and holes can actually be modified by a technique called doping. So as we can see, the Fermi level actually moves with the doping level. So for a doped semiconductor, the Fermi level is not a good reference point for the analysis. So what we do, we introduce a new thing called as the intrinsic Fermi level, which is denoted by EI. So we use this as a reference point in our analysis. So what we do is we find what is the relative position of EF with respect to EI. So if EF is above EI, that means the concentration of electrons is increasing. On the other hand, if EF is below EI, that means the concentration of holes is increasing. So these are the four things that we draw in an energy band diagram. So the first one is the bottom of the conduction band. The second one is the top of the valence band. And the third one is the Fermi energy level. And the last one is the intrinsic Fermi level. So now that we know what these energy band diagrams contain, let's see what data we can actually gather from analyzing this diagram. So the first piece of information is we can actually find what is the type of material used. So that is based on the band gap of the material, we can actually find what is the type of the material used. So suppose if your band gap lies between 0.1 to 3.5 electron volt, then this device is a semiconductor. If the band gap is greater than 3.5 electron volt, it is classified as an insulator. So on a side note, metals do not have this concept of band gap. So what metals have is a partially filled band. So suppose this is the valence band of the material. This is the valence band of the metal. It is partially filled, which means that all the electrons in this partially filled band actually take part in current conduction. So therefore you do not have this concept of band gap in metals. Alright. So the second piece of information is what is the intrinsic carrier concentration of the material. So that is what is the default carrier concentration of the material without any doping. Alright. So mathematically, Ni actually is directly proportional to e power minus Eg by kT, where Eg is your band gap, K is your Boltzmann constant, and T is your temperature. So what this means is, if your band gap is higher, that means your intrinsic carrier concentration is lower. On the other hand, if your band gap is lower, that means your Ni is actually higher. So this actually comes out from the math, but a simple explanation for this is, suppose you have a wide band gap. That means your electron in the valence band actually needs higher energy to actually come to the conduction band. So the chances of creating this electron hole pair is actually lower in case of higher band gap devices. Whereas if the band gap is low, so suppose your conduction band is lower, that means the energy required for electrons from valence band to conduction band is actually short. So formation of this electron hole pair is actually easier. So therefore your Ni is actually more for your low band gap devices compared to wider band gap devices. Alright. So the next thing is, we can find what is the majority carrier concentration in the material. So like I mentioned before, we find what is the relative position between the EF and EI of the material. So suppose this is EI. If your EF is above EI, that means the majority carriers in this material is electron. And if your EF is actually below EI, that means the majority carriers are the holes. So one thing to keep in mind is this majority carrier concentration is actually exponentially dependent upon this difference between EI and EF. So even for a small change in the position of EF relative to EI, there is actually an exponential change in the carrier concentration. So these are the information regarding the carrier concentration. Next, let's see how we can estimate the voltages and electric fields developed in the device by looking at these diagrams. So suppose I have an energy band diagram that looks like this. So one thing to keep in mind is that these diagrams are actually drawn for electrons. So moving up is the increasing direction of energies. So we know that E is equal to minus Q times V. The negative is actually coming because we are drawing these diagrams for electrons. So from this relation we can see that if this is the direction of your increasing electrostatic potential energy, then this is the direction of your increasing electrostatic potential. So that means this is at higher potential compared to this. So basically you'll have a voltage difference that is developed in this direction. So now that we know what is the polarity of this electrostatic potential, we can actually find what is the direction of the electric field. So it is from the positive to negative terminal. So now that we know the electric field, we can actually see what is the force. So suppose you have an electron at this edge, that means your force will actually push your electron down this hill. Alright. So this tells how the electron actually moves along this energy band. So now we know the direction of electric field. We can actually also estimate what is the magnitude of this electric field. So E is actually given by dV by dx. So from this relation we actually know V is equal to minus E by Q. So if I substitute it, it is actually d by dx of minus E by Q. So basically what this is telling is the slope of this energy band diagram actually gives the magnitude of this electric field. So what it means, so as I'm moving from left to the right, we can see at the left the slope is 0. That means your electric field is actually 0. So as I am moving at this edge, your electric field starts increasing. So at the center the slope is maximum. That means your magnitude of electric field is maximum at the center. And as I'm moving towards the right, the slope decreases. And finally the electric field goes to 0. So here it is 0 and here it is 0. So this way we can actually find what is the magnitude of the electric field. So these are the information that we can actually get by just analyzing the energy band diagrams. So now that we know what data we can actually get from looking at these diagrams, let's take an example and see how all these fit together. Alright. So assume that I'm given this energy band diagram. Let's see what information we can extract from this diagram. So the first piece of information is we can see that the band gaps on both the sides is the same. That is, the band gap here and the band gap here is the same. Suppose if the band gap is 1.1 electron volt, then on both the sides we have used silicon. Next we'll see what is the relative position of EF with respect to EI. We see that on the left the EF is above EI, that means the majority carriers are electron. So that means this is n-type silicon. On the other hand, on the right, we see that your EF is below EI. That means your majority carriers are holes. So that means this is a p-type silicon. So as we can see, as we move from the edge to the center of the device, we see that the distance between your EF and EI keeps reducing, right? This means that the carrier concentration is actually reducing as I move towards the center. Similarly, if I come from right towards the center, you notice that the EI and EF distance is actually reducing. This means that the concentration of holes is actually reducing at the center. So we can see that at the center, your carrier concentration is very less. So this is what we actually refer to as the depletion region. So now we got to know how the carrier concentration actually changes as we move from one end to the other end of the device. Now let's see how is the voltages and electric field developed in this device. So the first thing we can say is that this is at higher potential compared to this. So that means there is a potential difference that is developed in this direction, which also implies that you have an electric field in this direction from positive to negative. So this means that if you have any electron that is at this edge, it will be pushed down this hill. You can also actually find what is the magnitude of this electric field. So that is by finding the slope of these energy bands. So we can see that at the edges your electric field is 0. The magnitude of electric field is 0. So as I'm moving towards the center, your slope keeps increasing. So at the center, your electric field is maximum. And again, as I move away from the center, your electric field actually goes back to 0. So just by analyzing this simple energy band diagram, we could see what is the type of device that is being constructed and what is the carrier concentration along the device, and see how the voltages and electric fields are developed in this device. Alright. So this is the power of using energy band diagrams in analyzing device physics. So before I end this video, I want to point to one reference paper which actually gives the importance of these energy band diagrams in case of heterojunctions. Alright. So this is a Nobel lecture paper in physics, so which was given in the year 2000 by Herbert Kromer. So he mentioned something called the Kromer's lemma of proven ignorance. So what he tells that is, if in discussing a semiconductor problem, you cannot draw an energy band diagram, this shows that you don't know what you are talking about. And with the corollary that, if you can draw one, but you don't, then your audience won't know what you're talking about. And this statement is very much important when you are trying to analyze heterojunctions. You can actually read this paper, which is actually a very good read. But this statement is very true when you're trying to analyze heterojunctions, because most of your understanding comes down to how well you can actually draw these diagrams and how well you can actually interpret them. So that's the end of this video. If you want a brief introduction of semiconductor physics and you want to understand where all the topics in this subject actually comes together, you can refer to my first video on the introduction to semiconductor physics, which I'll link it down in the description. So that's the end of this video, and thanks for watching, and see you in the next one.